Hello and welcome. I'm Tyler and I'll be going through recommended problems 32 and 33 in chapter 4 from the Hibbler textbook. In the textbook, we were given this pipe-like structure coming out of point A on the X, Y, and Z coordinate system. We know the force F is acting on point C, and we know the distances relative to the points between them. We're asked to find the moment of this force about point A and then about point B. So here I've modified the problem, and here's the table to show you exactly what I've modified. So I've modified the force in every component. I've changed the direction of it, and I've increased the length between A and B, A and C, and B and C. I've kept the question the same. So we're still determining the moment about point A and then point B. So here's a sketch, and this kind of breaks it up so we can easily see the coordinates. This one on the left is a little harder to determine, and on the right, we can easily determine point A, B, and C and their coordinate. So let's go ahead and break up this force into its component parts. So here we can clearly see the components, and that's described with this Cartesian vector form. The problem is asking us to find a moment. So a moment is a force times the perpendicular distance around a specific point, and we're asked about point A. So, for example, if we were to move this force to point A, the force stays the same, and so do the components. However, it's not describing the same thing. So these things do not equal each other. Instead, we have to also add what's known as a moment force. So moments are generally drawn with a double arrow, or they're used on 2D with counterclockwise or clockwise. And then those would be equal. So what do we have to assume? A moment is a force multiplied by a perpendicular distance from the axis. And then we use the right-hand rule to determine the positive direction of the rotation of the moment. So what does that mean? That means when we use our right hand and we point our thumb in the X, our index finger in the Y, we put our middle finger towards the Z. And these are all the positive coordinates. Okay, and then what we do after that is we point our thumb in the direction of the moment and we curl our fingers inwards. And that's going to tell us what direction this moment is moving in. So how do we calculate that? Well, we know that the formulas, and this is provided in our statics worksheet, and we know that the moment is equal to the cross product of the position vector and the force vector. In our case, this will be t. And then we just plug in all the values for the I, j, and k. And then the way we find the position vector is the final point minus the initial point for x, y, and z. So again, here's our given. We're given the equations. Now we can determine the points using the figure on the right. So A is going to be our origin, so 0, 0, 0. Our B is moving 6 meters in the positive x direction. And then our C is the 6, 9.5, and -2. We're also given our t vector. And these are all using the correct units, and I've indicated those on the outside. So here's the solution. So we have all of our knowns, and then we have our image here. This is just for reference. And you'll notice I've indicated this counterclockwise looking arrow, and that's determining which direction is the positive moment. So that I use that getting our right hand right-hand rule determines this direction, and from there we can move forward. So first we need to find the position vector. So that's going to be the final vector c minus the point A, which is the origin. So its position vector is here. And then we plug that into our moment equation and expand it out. We have two vectors crossed with each other. And then from here, it's pretty simple once they're in the Cartesian vector form. We can just easily plug in these. So this is asking for ry. This is our ry. Then it's multiplying by the fz. So our fz is here. And then we just continue doing that for the rest of this equation. And this is what we end up here. All right, and then using basic algebra, we can calculate it, and we can find that our moment is this. This is our Cartesian vector form of our moment. So that's 32. It didn't ask, but I've included an image of what a moment means. So the moment is acting at point A. We're indicating the moment using the double arrows here. And you can think about it like if you put your thumb in this direction and then you curl your fingers, that's the direction the moment is moving. We can also break this up into its component parts and see exactly what the moment about each axes. So here's problem 33. The vector's the same. The only thing that changes is what point we're determining the moment from. So here we find the position vector first. The only thing that changes is the x direction, and then we plug that into our moment, basic algebra, and we can determine our moment about point B. And you'll notice that the x coordinate has not changed at all. And that's because we're moving along the x-axis here. So the perpendicular distance of the y and z does not change, so neither does the x. So here's the moment for point B and the components of the moment. And here are our final answers. I hope you learned something. I hope it's helpful. Thank you for watching.